What if the macro world was like the quantum world? Well, our ancestors believed that the macro and micro universes were pretty much the same, with the same laws of physics. Even Einstein was a strong supporter of this idea. But then quantum mechanics came and changed everything. Really, changed everything. We realized that the rules of the quantum realm were nothing like that of our daily life. There was some spooky action at a distance, and God playing dice, and some real weird stuff. But within this chaos of subatomic particles, we found some real eye-opening answers. In today's video, we would discuss what if the laws of quantum mechanics applied to our daily life. So without any further ado, let's begin the video. Quantum superposition. In 1935, a great scientist with an unexpected resentment towards cats carried out a thought experiment. Erwin Schrödinger's thought experiment went like this. A cat is kept in a box along with some nuclear material with a 50% chance of decaying and killing the cat. After the box is closed, there is no way you can see through the box or hear what is going inside the box. Schrödinger then posed the ultimate question. When the box is closed, is the cat dead or alive? Answering his question, Erwin Schrödinger came up with a revolutionary answer that stated that the cat is both dead and alive at the same time. Here, the cat is a metaphor for a subatomic particle, and the experiment symbolizes quantum superposition. It means that if we have a particle in a container, it could be at any place until we observe it. If this would happen in real life, life would be very strange. For example, you are at a restaurant and ask the waiter to bring you any kind of cold drink. Now, until the waiter serves you, the waiter is bringing all sorts of cold drink at the same time. Now, when the waiter arrives, you get only one of those different kinds of cold drinks. Mind-boggling, isn't it?
Quantum entanglement. Well, what is quantum entanglement? It's some spooky action at a distance where a pair of particles are generated and interact in such a way that the state of one particle cannot be described independently without the other particle, and this applies to even large distances such as the size of the observable universe. If it happens in the real life, we would have entangled coins. Let's take two coins A and B and assume they are entangled with each other. If we flip a coin, we will get one of the two outcomes, heads or tails. Let us say coin A is heads. Now by quantum entanglement, coin B has to be tails simultaneously. They will always be opposite to each other instantly and can never be the same. Fun fact, if coin A is at one end of the observable universe and coin B at the other end, when coin A is heads, coin B will instantly be tails. So the speed of communication between them would be exponentially greater than the speed of light.
Uncertainty principle. The uncertainty principle states that you can never know the momentum and position of a particle at the same time. The more accurately you know one property of the particle, the more your knowledge about the other property is jeopardized. If this would apply in a real world, the job of a traffic police would be really difficult. Please note that in real life, by our technological standards, it is impossible to see a noticeable change in the mass of an object. So here we would replace momentum with velocity. Back to topic. It would be very difficult for the policeman to issue a fine for overspeeding, as if he knows the speed of the vehicle, he would not know where the vehicle is, and if he knows where the vehicle is, he would not know the speed of the vehicle. Doing that job would be living in hell. Quantum tunneling. Imagine a boy playing under the sun. He has a ball and wants to send it up the hill. He gives it a little push, but the kinetic energy of the ball cannot overcome the gravity acting on it, and hence it rolls back down after going forward. Now we will see this from the quantum world perspective. Let's replace the ball with a quantum particle and the hill with some sort of barrier. Even if the particle does not have enough kinetic energy to go over the barrier, there is still a small probability that the particle will be found on the other side. So what would it be like in a real world? The ball might have ended up on the other side even with little kinetic energy if it had been tried many times. It is good that there are separate laws for the micro and macro world. We don't have such complex daily lives, and we also enjoy the wonders of the subatomic world. We would end our video with a quote of the great scientist Niels Bohr. If you aren't confused by quantum mechanics, you haven't really understood it. Thanks for watching. If you enjoyed the video, hit the subscribe button to get more content like this.